a quick recap of what we were doing in the last class. We were looking at the concept of reciprocity, interreciprocity in linear periodically time varying systems. The network was assumed to be LPTV and varying at a rate Fs. We assume that it only consists of time varying conductances, capacitors and inductors, and yesterday we showed that if port 1 of n was excited with e to the j 2 pi f t and the output voltage at port 2, apart from having a whole bunch of tones at frequencies f plus integral multiples of f s, it will also have a tone at f, and that transfer function is h 0 of j 2 pi f f t plus other terms. What we saw yesterday was that if we formed, so if we call this g of t, if we formed the so called adjoint or the interreciprocal network, which we call n hat, where all the inductors remain the same, all the capacitors remain the same, and all the conductances are replaced by g of minus t. So, this g of minus t is sometimes also called the time reversed version of g of t, and you excite the output port with a current e to the j 2 pi f t, and then it turns out that the voltage developed at cross port 1 is h sub 0 of j 2 pi f e to the j 2 pi f t plus other terms, right. The key point is to note that the zeroth order harmonic transfer function from the input port to the output port is the same as the transfer function from the output port to the input port in the adjoint network or the interreciprocal network. All right. We will see why this is significant in a little while, but this is what I want to point out. So, yesterday we couple of we did not discuss control sources. Right, and remember that the key to realizing or deriving the adjoint network was to recognize that the M&A matrix of n has an M&A matrix G, and n hat has an M&A matrix of G transpose. All right. So, now the question is, if we have control sources, what do we do? Well, G is simply formed by adding the M&A stamps of the individual elements. So, if you have controlled sources in the original network G, then you need to replace it with an element whose M&A stamp is the transpose of that element, right. So, again, so the idea is very simple. You just replace a controlled source in n with an element whose M&A stamp is the transpose of that element. All right, and so let's do this. So let's say you have n, and you have a controlled source like this. Remember that if you have a time varying network, the gain corresponding to the controlled source or the transconductance or whatever can also be time varying. So, we have 4 nodes A, B, C and D, and this current is simply G m of t times V of A minus V of B, correct. So, this is a periodically varying control source, voltage controlled current source, right, and G m of t equals G m of t plus T s, right, and this can be expanded in a Fourier series G m sub L e to the j 2 pi L f s times t, just like the time varying conductance, right. So, what do we do? Well, the idea is very similar. The MNA stamp of the periodically time varying current source is going to look like this. So, if this is the G matrix, this is there is going to be something which only depend in rows C and D, right, because the current is only flowing between C and D, and between nodes in the columns A and B, because that is the voltage dependence. And if we write and again if we write this in terms of the current in terms of the phasor vectors, then the current flowing here is we call that I of t, and its current corresponding phasor is I, then this is nothing but the G m matrix times the phasor V A at A minus the phasor at B, where G m is a matrix, right, which is of size 2k plus 1, 2k plus 1 cross 2k plus 1, right, and this is G m 0, G m minus 1 all the way up to G m minus 2k, this is G m 1 blah blah blah, this is G m 2k, and this is G m 0. All right. And so, what will the MNA stamp be? This will be G m and minus G m, this will be minus G m and this will be G m, all right. And this therefore is the MNA stamp of the voltage controlled, of the periodically time varying voltage controlled current source. What do we need to do in the we now need to find its transpose, right, and what will the transpose look like? Well, if it appears in the 8th and bth columns, it must appear in the you can see that this entry, for instance, appears, it's a block matrix, but it appears in the cth row and the 8th column. So, now it must appear in the 8th row and the 6th column, right. So, this, and it must be transposed, all right. Similarly, you must also have, so this must be C and D, and you will have GM transpose and minus GM transpose, this is minus GM transpose. Okay. So, in this in the 8th row you have GM transpose and minus GM transpose, and in the bth row you have minus GM transpose and GM transpose. So, what comment can you make with regard to the element? So, this is the MNA stamp. So, we started with the element and we wrote the MNA stamp, we transposed the MNA stamp. Now, we need to get back to the element, and how does that look like? So, well, this looks like a, it's a voltage controlled current source, except that the, yeah, very good, the ports are interchanged, the controlling and current control ports are interchanged, that is one change. So, that is basically GM, the currents are flowing between nodes A and B, and the controlling voltages are nodes C and D, all right. So, this is GM of, I mean, what comment can we make? Now, the matrix corresponding to the time varying gain is the transpose of the original one. So, what comment can we make? It must be time reverse. So, this is GM of minus T times Vc minus Vd, right. So, this is the replacement that we must do in the to get the adjoint, right. This is very similar to what we did in the time invariant case, except that there is the additional step of having to time reverse the gain. If the gain is fixed, of course, then it is exactly the same thing. It does not, I mean, if GM of T does not vary with time, whether you flip it in time or not does not matter. But the key point is that you need to do two operations. One is to flip the controlled and the controlling ports, and you time reverse the gain. Okay. So, that takes care of the voltage controlled current source. Now, I think you get the basic idea. I mean, it's the rest of it is very straightforward. Let us say we have in N, we have a voltage controlled voltage source. So, this is A, this is B, this is C, and this is D, and this is mu of T times V of A minus V of B. Mu of T is the same as mu of T plus Ts, which is again sum over L, mu sub L e to the j 2 pi LFS times T. All right. And what is the MNA stamp? So, you have I of T, right. So, what do we do when we have a voltage controlled voltage source? We have to have an additional so we add an auxiliary variable which is I of T, right, and you have an auxiliary equation. So, Vc, the auxiliary equation is Vc minus Vd equals mu of T times V of A minus V of B, all right. and therefore, in the phasor vector notation, this will be V c, the V c vector minus the V d vector must be the matrix mu times V a minus V b, right. And remember that V c, V d, so V a blah 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 V d are 2k plus 1 cross 1 column vectors. And the matrix mu is again mu 0 blah 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 mu minus 2k. Did we have minus 2k there? Yeah. So, it should be mu minus 1 blah 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 mu 1 blah 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 mu 2k, that is mu 0. All right. Okay. So, what is the M&A stamp? Well, in rows C and D, right. So, basically we have this additional stuff for this variable, which is I of t, and that we basically we say we have now a matrix 1, okay, and this is a matrix 1, right. So, this one is what kind of matrix? No. See this I, what comment can we make about the phasor vector corresponding to this I of t? This is a column vector with 2k plus 1 rows, right, which basically quantify the strength of each harmonic in that in I, right. So, that I must be added as it is to each row. So, what must you multiply it by to get
corresponding voltage?
You have
Diagonal.
this I therefore is a identity matrix of size 2k plus 1 cross 2k plus 1. You understand?
Yeah.
So, this is plus 1 and this must be minus 1. Right. So, the ones in this matrix are basically 2k plus 1 cross 2k plus 1 identity matrices. And what do we do about the last we need? So, we have an extra variable, and therefore, we need an extra equation. And what is that extra equation? That is simply saying that mu times, so the vector must be in row A, row B, I mean column A, column B, column C and column D. So, you basically have the matrix mu, the matrix minus mu, right, minus 1 and plus 1, right. And remember that all the ones that you see in this M&A stamp are diagonal matrices. So, I mean this is very similar to what you would get with a time invariant one, except that now we have instead of dealing with the numbers, you have matrices, that is all, right. Even writing the M&A equation is very straightforward. Once you generate the mu matrix, it is just simply plopping that into the big matrix. Now, so now what do we need to do in the, if we need to generate the adjoint, an element whose stamp is the transpose of this. So, this is the transpose. To transpose, what do we do? Well, what will you get? whatever is there in the row will become the column and vice versa. So, what do you expect to see? Well, we need to have, there will be some entries in the 8th row, the bth row, the cth row and the dth row. And what will the entries be? There will be mu transpose minus mu transpose. Well, the diagonal matrix is anyway the same. So, minus 1 and 1. Okay. And what comment can you make about the last row? Well, that will have entries only in the cth and dth columns, and that will be in C it will be 1 and D it will be minus 1, right. So, what is the last row now telling us? That last equation is telling us that V c equal to V d, right, and the
last column will telling the voltage.
It is telling us
Like extra equation.
Correct.
That is like Vc minus Vd equal to
Correct.
mu times Vm.
No.
Mu transpose.
No. Well, I mean, if you have an MNA stamp like this, what is this telling us? I mean, see, every time you add an extra column,
That is the current.
you are drawing current from nodes A and A, B, C and D. So, this is nothing but a current controlled current source, where the so basically this is V c is equal to V d, right, and this is a 0 voltage source, and this is A and this is B, correct, and the current that is flowing is
That is the current control voltage.
current controlled
Current control current source.
right. So, this is the controlling current, all right, and what is this current, how is that current related to this controlled current?
Mu times I of.
Mu is varying with time. So,
Mu of t, mu transpose, mu of minus t.
mu of minus t, all right. So, this is mu of minus t times I of t. Right, because this is the MNA stamp of a current controlled with gain mu of minus t. All right. So, this is the substitution that you must make, all right, when you go from the real network to the adjoint network. Now, so I am not going to derive the other two. What we will do is simply write down the final result. So, if we have V c V s, you have to replace it by a C c C s, right. If you have a, so summary so far is voltage controlled current source gets replaced with a voltage controlled current source. If this is G m of t, this is G m of minus t, and controlled and controlling ports are interchanged. all right. All right. Now, voltage controlled voltage source mu of t gets replaced by a current controlled current source mu of minus t, again with controlled and controlled source, controlling ports interchanged. All right. Now, by the same token, a current controlled current source with a gain of mu of t, what will you do?
Current control will become voltage control.
Voltage controlled voltage source with a gain
Mu of minus
mu of minus t,
ports
and again
ports are interchanged.
with the controlling and control ports interchange. All right. And finally, the only thing that is left over is the current controlled voltage source with a gain, which is with a time varying trans impedance R of t. So, this is this is node A, this is node B, this is a current controlled. So, this is I of t, and this is C, and this is D, and this is R of t times I of t. Right. So, this is the network in N. What should you do in N hat?
It is the voltage current control current source.
This is a current control voltage source. So, what will you have in the adjoint? This will be
CCVS.
it will be a CCVS, that is this is going to be R of minus t times I of t. This is N. And this is what you will have in N hat. All right. So, to summarize, if N now has got G of t, L, C and control sources, this is N, and we have the input port and the output port. Then what we will have in N hat, we know how to form N hat. This is G of minus t, L, C and control sources. And what is the difference between these control sources and those? Appropriate replacement then input and output ports are flipped. Okay. And gain or transimpedance or whatever is time reversed. Okay. This is 1, this is 1 prime, this is 2, this is 2 prime, and therefore, if I inject a current T, I will get H sub 0 of j 2 pi f t, H sub 0 of j 2 pi f times e to the j 2 pi f t plus other terms. And likewise, if I interchange the location of the excitation, what I will get here between ports 1 and 1 prime, I will get the same thing, which is H 0 of j 2 pi f e to the j 2 pi f t plus other terms. Okay. But I would like to point out that these other terms and these other terms need not necessarily be all right. All that we have proved is that these terms are equal. Okay. So, this is what is called the transfer function theorem. Right. It is not necessary that the exciting quantity is a current and the output is a voltage. You can also have other pairs of you can have other pairs of input sources, and so for example, if the output was a current rather than a voltage, the output current would be H 0 of j 2 pi f times e to the j 2 pi f t plus other terms, right. So, what comment can you make about what we should do in the adjoint network?
You have to apply the voltage.
We have to apply?
Voltage.
Yeah, current controlled, current gain in the original network will be equal to a voltage gain in the adjoint network. So, this will be e to the j 2 pi f t, and the voltage you will measure across port 1 will be H 0 of j 2 pi f times e to the j 2 pi f t plus other terms. Okay. Does that make sense? Okay. So, this is what you see if the and likewise if the original network has a voltage gain, then in the inter-reciprocal network it will be the current gain, and if you drive it with a current and you measure the sorry, we have driven it with the current and measured voltage and current. We have driven it to the voltage, measured voltage, right, and if we, the last thing is that you drive with a voltage so let us say you drive it with a voltage so this is e to the j 2 pi f t and you measure current this is h 0 of j 2 pi f e to the j 2 pi f t plus other terms. And what do we do on this side? You drive with a voltage, measure the current. Very good. This is h 0 of j 2 pi f e to the j 2 pi f t plus blah blah. All right. Does that make sense? Right. So, I mean this again there is nothing particularly new here. We knew all this. I mean whatever we did, we only proved the result for this case, right, but the same, I mean you can do the same run through the same proof for any of the other four other three types of excitations, right, excitation response combinations. So, that way there is nothing particularly new. The only key, I mean the key point is to observe that when you create the adjoint, you have to time reverse the time varying components, right.